Hi everyone, welcome once more to this YouTube channel at Best Science Brain YouTube channel. Today we're presenting solution to NECO June 2024 May June examination. So in this practical today, our focus is going to be on quantitative or volumetric analysis, also known as titration. So we're going to determine the endpoint based on the specimen provided. We are given specimen A, which is a 3.8 centimeter cube of H2SO4, and specimen B, which is 6 grams of sodium and hydrosodium carbonate. So we're going to run the titration and obtain the correct endpoint, after which we're going to trace some calculations, some speculated calculations. We're going to take about three different questions on this particular specimen. So as a student, you advise not to copy solutions verbatim, but copy and learn how it is being done. That you're giving H2SO4 and sodium carbonate at the specimen does not mean that in the question paper that you must see the same concentration we're going to use on the calculation here. Remember that NECO has every right to change the chemical or change the concentration on the question paper. Perhaps you're giving sodium carbonate in the specimen, and in the actual question you're seeing sodium hydroxide. It's possible, just like what happened in WAEC this year, whereby the teachers were asked to prepare iron sulfate, and they provided impure iron granules as specimen B. So today we're looking at this practical, and then you have the format for reporting the result. One over our pipette use 25.00 cm cube, indicator use methyl orange, color change yellow in the alkali and orange at the end point. Bullet readings: first reading initial, develop of A, like data values, rough 1, 2, and 3. So we're going to run the experiment and then you watch us as to do that. So we're looking at NECO June 2024. The question we speculated for this practical. Say A is a solution of 0.0699 mole per dn cube H2SO4. B is a solution of H2CO3 containing 3 grams of the substance in 500 cm cube of water. Put A into the burette and titrate with 20/25 cm cube portions of B using methyl orange indicator. Repeat the experiment to obtain consistent readings, tablet readings. Then A says calculate the average volume of A used. So before we go to the calculations here, we're going to do the experiment first to find the end point. So we can see that the acid level have been leveled to 0.00, the initial value. So report initial value under rough as 0.00. So we're now going to pipette the alkali into the conical flask using the pipette. So we'll now move ahead. So this is our pipette. Then we prepare the alkali. Then, okay. You can see it going down gradually to the meniscus or to the ring. We'll stop there. We'll take it up. Bring a neat conical flask. It has gone down, so we'll have to add more. So adjust your hand, allow the air to enter, and what the meniscus, the bottom of the curve, as it's going down to sit on the ring. Oh. Gradually. Okay, we're going there. So we are there. have 25 exactly now. So you now move it to the conical flowers. Allow it to move to the conical flowers. That is the solution B. Having done that, you now drop. Then get your methyl orange, freshly prepared. Use a dropping pipette. Collect only 2 drops. 1, 2, because indicators are weak acids or weak organic bases. So you only add 2 drops so that you not affect the end point of the reaction. So you see the yellow color. So we're about to start the titration with acid level at 0. Bring a white tie under and bring the conical flowers under. And then we'll start titrating. We'll allow the acid to run into the conical flowers drop by drop. As it's going, you shake your flowers. You can increase the drop. Because this is the first one you're doing, so you have to be very careful of the color change. So you can use a white tie under, but we're using an improvised white tie, using a filter paper. You can still use an A4 paper under. So the essence of the white tie is to know when the color changes for accuracy. So that if the color changes, it reflects on the white tie. So let me increase it a little. You swire your flowers. Continue titrating. So let me allow it to be dropping little by little. While I tighten my burette. Okay. It's going little by little. It's still yellow in color. Then increase the pace a little and know when the color will change. So I'm looking at the white tie, observing the color change. You're going step by step. So doing the first one will give you an idea of the end point. So you allow the first one you're doing to go little by little. So when you do the second one, you can now increase your pace or increase your speed. So that is it. Make sure that the tap is not leaking. That's what are the precautions. The precautions for the experiment is that you make sure the burette is clamped vertically, erect. You also make sure that the burette is rinsed with the acid that you're supposed to use for the titration commences. You also make sure that the conical flask is only rinsed with distilled water. You also make sure that you only add 2 drops of indicator, 2 or 3 drops of indicator, the experiment. Because indicators, as I said, are solutions of organic acids and organic bases or dyes. So if you add plenty amount of the indicator, you're going to affect the end point. So you also make sure you place a white tie under the conical flower during titration. The white tie ensures accurate color change. So the white tie gives you sharp color change. So when there's a color change, it reflects instantly on the white tie. So these are some of the precautions you observe while doing titration experiment. So I'm watching the color as well as watching the burette reading. And then your main focus should be on the color and then not on the burette reading, because the burette reading, the color, you observe the color not on the burette, you observe the color on the conical flowers. So you see yellow as we continue to move it and see going drop by drop. You see you have to take some patience so that you know when the color changes. So we're observing this. You're still watching Best Science Brain YouTube channel. So if you are not subscribed to the channel, as the video is playing, move down beneath the video. You see the channel's name, Best Science Brain. And you see the subscription icon that looks like a small bell. Tap on the bell only once and get subscribed to the channel. Tap on the bell only once and get subscribed to the channel. So you are moving closer, the color is changing somehow, getting somehow darker, moving closer. So we'll stop it and shade. The color had changed. So you can see we have an orange color here. So the color change at, if I read it, is at 25.6. 25.6. So you see this is different from yellow, orange, glittering in color, in appearance, orange color. So we'll now go to the board and report final reading on rough 20.60. 20.60. Now the color change. We'll now subtract 20.60 minus 0, that give us 20.60. We'll now go to the first experiment. What do we now do? We'll go to the burette. We're going to empty this one. So after you empty the titration mixture, you rinse it with water, distilled water only. As I say, rinse the conical flour with distilled water only, because distilled water has pH of 7. That will not affect your endpoint. Rinse it and then you pour it off. So we are topping more of A into the burette. We're adding more. Adding more of A into the burette. And we adjust again. Before you adjust, remove the funnel, because the funnel, if you keep it there, you're going to add additional drop into the burette. So remove the funnel and adjust. You may wish to start from 0. You may wish to start from 1. Let me adjust to 1. So it must not be from 0 now. So I'm adjusting to start from one whole number. So that is 1 there. So now report on the board. Initial here is 1.00. So the next thing we're going to do is we're going to pipette the base into the conical flask and then repeat the titration again. So we're going to, this is the base already in the pipette. So move your hand a little to allow, that's much, to allow the base. So we adjust the base little by little. It's going down slowly. If you have a suction pump, you can still use it using your mouth. You can as well use a measuring cylinder. We'll have it there. So you just drop it at the bottom, take it up, don't blow the last drop, and then remove your hand, empty it into the conical flask. So having done that, drop, just stick it at the bottom. We now get the indicator, collect fresh prepared material range, take only 2 drops, first, second, of the material range into the base, turn it, check it, it is yellow in color. So next is we start the titration experiment. So now we'll start the experiment. Remember our initial is 1.0. So we allow the acid to run drop by drop into the conical flask where you have the base and the indicator. So as an estimate, we'll go to the board. Since the titer value we have for the rough is 20.6. So if we should put 20.6 here, 20.6 there, sorry, the final reading is going to be 21.60. But these values are not, I didn't say they are correct. I said, let's assume that this is correct. We put 20.6 here, the final is going to be 20.6 plus 1, that gives us 21.6. And then you have to estimate. That means you're going to run the titration to 21.6. But you don't have to reach 21.6. The next whole number before 21.6 is 21. So you're going to run titration until the final reading is 21.00. So once you reach 21.00 at the final, I will close the tap and then take it drop by drop. Definitely, the color will change between 21 and 22. So let me clean this place off. So you can estimate your reading as you're doing this experiment. Since we are very careful when we did the first one. So let's go back to the titration. So we can increase the rate a little. Is 3.70. So I like to go slowly and see when are you going to reach 21. So when it reaches 21, I will close the tab. Then after closing the tab, I'll take it slowly and then move to the end point and observe the color very well. So it's moving to 5 whole number. So as we said, you're still on to Best Science Brain YouTube channel. And this is NECO 2024 specimen. Solution A is contains 3.8 cm cube of H2SO4 acid. Solution B is 6 grams of anhydrous sodium carbonate. So that is the iteration we're performing, trying to verify the end point or the accurate end point. If you're not subscribed to the channel, and the video is playing right now, move beneath your video and then look for the channel's subscription button. Under the channel's name, Best Science Brain, you have the subscription bell or icon. Tap on that bell only once and get subscribed to the channel where we treat chemistry and physics topics. So, as we're moving on, gradually we're approaching 8. So we're moving on and to see when the color will change. So they take it slowly and see. We're going to have the solution or have the accurate endpoint. If you wish to contact us on this channel, you can email us. The channel's name and email displayed as you're watching this video. Our email remains bestsciencebrain@gmail.com. Let's say you want us to provide tutorial or lesson for your students performing writing WAEC or NECO examination or a private tutorial. You can email us on bestsciencebrain@gmail.com, or a direct message which you can get at the quickest time. You can send direct message to Best Science Brain YouTube, Best Science Brain, not YouTube, Best Science Brain Facebook. So search us on Facebook, Best Science Brain Facebook. You also see Best Science Brain Facebook page. They will have a page. You also have a Best Science Brain group. The page is for those in higher institution, while the group is for those at O level. So whichever one you send your inbox message, you're going to see it. So I increase the pace. So you see it's moving faster. So we're moving faster. And then we're approaching 21. We're approaching 18 now. 18. We're moving to 19. Okay, moving to 20. Moving to 21. So we are 21 now. We now open the tab so that it will go in out gradually. We'll pause it at 21 and then we'll have to take it drop by drop until have an accurate color change. So we'll now close the tab and then shake it. So we'll have the color change. You have a glittering orange color change obtained. So we'll take a reading from the burette. The burette reading is 21.30. 21.30. So we'll have final 21.30. We'll now subtract. We're going to have 20.3. So you see that this one is less than this, showing that when we did the first one, we overshot the acid. So this is more accurate now. So we're now going to pour away this titration mixture and do the next experiment. So we're topping the acid again for the second titration. So now I wish to start from 5 whole number. Choose any whole number of your own convenience to start from. So after you added the acid, remove the funnel. The funnel As the precautionary measure, the furnace will be removed because the furnace should be, if you leave it there, you're going to be adding additional drop of the acid. So let me adjust the acid to 5 whole number, or we should start from 5. So it's there. So I'll close the tap. Okay, firmly. So having, okay, it has gone a little. Let me add more of the acid to make it up to 5. So it's above 5. Adjust again. And measure the bottom of the meniscus sits on 5. The bottom of the curve you're seeing, the concave shape, sits on the mark for 5. It's going gradually. So here we are there at 5. So record our initial read on the board. Here, record 5.00. That is 5. Then, should the correct endpoint be 20.3 at this point? So we expect it to change at the 2. We expect to change at 25.3, 25.30. So by estimation, by calculation. So all it means is we're going to run the titration until reach the nearest whole number before 25.3 is 25. We are rather to run to 25. When we reach 25, we now stop the tap and take it drop by drop. So we clean up and then do the experiment again. So we started from 5 is going down. So we expect, as we said, we expect to run it to around 25. So we can increase the pace a little and we'll be watching it. So when it's 25, we'll close the tap and then take it drop by drop and see where it's going to change as we expected. So we are 17 is moving, getting to 18, going to 19 now, going to 20, going to 21, going to 22, 23, 24, then it's going to 25. At 25, I have to stop the tap. As I stopped it now, then I like to go drop by drop, let one drop at a time. You see the way it's going? One drop at a time. So gradually another drop, because one drop is about 0.1 cm. Okay, so that is all right. So let's check the color. So bring out the icon and check it. You still have an orange color produced. Definitely an orange color. It's glittering color of 10, 25.30. So go to the board and record 25.30. So when we subtract, we have 20.30. All your values should record to 2 decimal places. So what you're reading, all of them 2 decimal places. Unit of measurement must be indicated on the table. So cm cube indicated. You don't have to write it 3 times. I didn't say cm. I did not say cm square. Cm cube. Then your values all to 2 decimal places. So can we do the third one? We don't need to do the third one since the first and second are the same, consistent. So since 1 and 2 are the same, you don't have to do the third one, please. So what we have to do is we calculate our VA. Our VA is now given as 1 plus 2 over 2, not over 3, because we do not use 3 theta values. We use the first and the second. So the rough is far, so ignore the rough. Since the value of the rough the range is wider, is much. So use first and second. So now have 20.30 plus 20.30 divided by 2. But perhaps if you did your own 3 times and they are in agreement by plus or minus 0.2, you now use the 3 of them and divide by 3. So your VA now becomes equal to 20.30 cm cube. So that's the end point for this NECO 2024 June-July chemistry examination. So before we go to our calculations, we look at the endpoint we got VA 20.30. We're going to advise students. Number one, this titration examination is being marked based on what the teacher recorded as the endpoint. Your school teacher, what recorded as the endpoint. So as you're watching this channel, don't use our endpoint unless it agrees with what your teacher recorded. If your teacher gave you a different value, then use your teacher's endpoint, because you're going to be evaluated or marked based on your teacher's endpoint, because your teacher is going to fill a report form, and in that report form he's going to write his own endpoint. He writes 21, he writes 22, he writes 24. They're going to adjudge you based on your teacher's endpoint. Even though we obtained the correct endpoint, yes, but the examination body provides an avenue for students to be judged based on the teacher's endpoint, because if your teacher probably use an acid that is expired, or use an alkali that is expired, or use impure water, it will affect its endpoint. And since he prepared your solution with the same chemical, so you are not to be blamed. So they're going to judge you based on your teacher's endpoint. But if your teacher's endpoint is 20.30 plus or minus 0.10 of our own, then you can use our own endpoint. What do I mean? 20.30 plus or minus 0.1. That what it means, 20.30 minus 0.1 gives you 20.20. Then 20.30 plus this gives you 20.40. The middle value is 20.30. So minus 0.1, 20.2, plus 0.1, 20.4. So if a teacher gives you any of these endpoints, whether this or that, you can use our own endpoint. You see score maximum mark. So let's go to calculations right now. So we go to calculations. We have done the A part. Then the B part says, from your result and information provided, calculate the I constant of B in mole per dn cube, conc of B in mole per dn cube. So what information do we need? From the equation, we're given the conc of A as 0.0699. So let's go to the board. So we're looking for CB, conc of B in mole per dn cube. Our C again to us as 0.0699 mole per dn cube. Our VA from average titer is 20.30 cm cube. Our VB is 25 cm cube, the pipette we use. Then the mole ratio of A to B is 1:1. So since you know your CA, you apply the titration formula CAVA all over CBVB equal to NA over MB. So you go ahead and make CB the the formula. CB becomes equal to CAVAMB all over VB times NA. So make your substitutions. Your CA is 0.0699. Our VA is 20.30. Our MB is 1 all over. Our VB is 25. Our NA is also 1. So make use of calculator to find our CB. So we'll calculate. So after calculating, our CB is 0.0568 mole per dn cube. Leave your final answer to 3 significant figures. I didn't say decimal places. 3 SF or significant figures. 1, 2, 3 as your answer. So that's the value of our CB. We go to question BII. BII says relative molecular mass of S2CO3. So that S2CO3 is our B. So what do we need in the equation? We need to find the mass of S2CO3 given the equation. In the equation, we are told that B is the solution of S2CO3 containing 3 grams of the substance in 500 cm cube. 3 grams in 500 cm cube. So we'll now go ahead to find the relative molecular mass of S2CO3. So we are told that 500 cm cube of solution contains 3 grams of B. So therefore, we have to find the mass in 1000 cm cube. And that becomes our mass concentration. We now contain 1000 cm cube times 3 grams over 500 cm cube. So when we solve this, our mass concentration, our concentration in gram per dm cube, which we can call rho B. That rho is P, like P letter, B, is when you solve this, will give you 6.0 gram per dm cube. So, having done that, we know that concentration in mole per dm cube, that is which we call CEB, again by concentration in gram per dm cube all over molar mass. And we are looking for the molar mass of B. We make M the subject. So molecular mass of B becomes concentration in gram per dm cube, that is PB all over CB. So our PB is 6, while the concentration in gram per dm in mole per dm cube, which got in question BI, is 0.0568. So when we divide 6 by that, we're going to have 105.6 at the molecular mass of this substance. And since our final answer should be kept in 3SF, 105.6 will give you 106. Since its relative molecular mass, it has no unit. So if its molar mass, it would have been gram per mole. But its molecular mass, you don't give any unit to it. So 106 is the relative molecular mass of B, that is sodium carbonate. So question II says relative atomic mass of S, RAM of S, the element that is found inside S2CO3. To find the relative mass of S, we put the formula S, the formula of the compound S2CO3 to the molar mass, which is 106. So S is unknown. We now say 2 times S, since we have 2 atoms of S, plus carbon, atoms of carbon given to in bracket as 12. Oxygen again to as 16, multiplied by 3, since there are 3 atoms, equal to 106. We now have 2S plus 3 times 16 is 48, plus 2, that gives us 60, equal to 106. So 2L becomes 106 minus 6, that is collecting like 10 minus 60. So 2S gives us 46. So L becomes 46 over 2, and that gives us 23.023 significant figures. So relative atomic mass of S is 23.0, it has no unit. So we'll go to the next question. We'll now go to question IV that says percentage by mass of S in S2CO3. Percentage by mass of S in S2CO3. So before we do that, we have to go back to what we got in question II, which is the relative molecular mass of S2CO3, which is 106. Then the relative atomic mass of S, which we got in question BIII, is 23. So we have to find the mass of S inside this compound. So mass of S will now become, since there are 2 atoms of S in the compound, now becomes 2 times 23. So this is the mass of an atom, and there are 2 atoms, that gives us 46. So percentage of S in the compound will now become mass of S all over relative molecular mass of H2CO3 times 100 over 1. And mass of S is 46. That molecular mass is 106 times 100 over 1. And that will give us 43.4% to 3 significant figures as our answer. So question V says volume of CO2 liberated at STP during the reaction. Volume of CO2 liberated at STP during the reaction. So go to the board. So to calculate the volume of CO2 liberated at STP, we have to write the equation for the reaction. This is our CO2 which you're looking for. So our question mark will be on CO2. We'll connect CO2 to the carbonate. So we'll have 1 mole of the carbonate liberating 1 mole of CO2. We'll now write 1 mole of S2CO3 equivalent to 1 mole of CO2. And then, so now I have 1 mole of S2CO3 carbonate. We now change this to volume, which is 22.4 dN cube of CO2 at STP. Then we know that the molar concentration of this carbonate is 0.0568 mole per dN cube of H2CO3. We now liberate 0.0568 times 22.4, and that will give us 1.27 dN cube of CO2 liberated at STP. So having done this, we are going to look at the second question we have. We speculate for these particular practicals that have to do with solubility and other likely questions we expect from this particular specimen provided. So stay connected as we go. So we'll now look at another question for this particular practical that says solution A is H2SO4. Solution B is prepared by dissolving 0.75 gram of sodium carbonate in 250 cm cube at room temperature, which is 25 degrees Celsius, and diluting it to 1000 cm cube or 1 dN cube. Full stop. Put A into the burette and titrate with 20 or 25 cm cube portions of B using meteor range indicator. Repeat the experiment to obtain consistent readings. So we are not going to repeat the experiment, we have done the experiment already. So we are just going to the same specimen we did the titration. We got our endpoint at 20.30. We're going to the calculations. So first says calculate the average volume of A used, which we have done, which is 20.30. We're going to question B that says from your result and information provided, calculate the I concentration of B in mole per dN cube. Concentration of B in mole per dN cube. So we'll look for a clue. In the equation, we have solution A is H2SO4. Solution B is prepared by dissolving 0.75 gram of sodium carbonate in 250 cm cube at room temperature and diluting it to 1000 cm cube or 1 dN cube. So we're going to use this clue. We have 0.75 gram of sodium carbonate dissolved in 250 to calculate our CB. So we have to correct an error here. Solution B is prepared by dissolving 1.5, please, not 0.75, 1.50 gram of the carbonate in 250 cm cube. Solution B is prepared by dissolving 1.50 gram of the carbonate in 250 cm cube. So it's 1.5 we're using, not 0.75. So we have 250 cm cube solution B containing 1.50 grams. So therefore 1000 cm cube of solution B will now contain 1000 times 1.5 over 250. So that will give us 6.0 gram per dN cube. So this is the concentration of B in gram per dN cube, or the mass concentration of B. So to find the molar conc of B, we have to find the molar mass of B. So we have to find the relative molecular mass of sodium carbonate. You have to calculate it. Since in this question, the full name of the compound was given to you. So sodium is 23, multiplied by 2. Then carbon is 12. Also is 16, multiplied by 3. And that will give us 106. So if you relative, you don't have to put unit here. With molar mass, you put gram per mole over there. So your Cb becomes Pb over molar mass. Our Pb is 6, our molar mass is 106. So divide, we have, let's go to our calculator and get the final answer. So when we divide, we're going to have 0.0566 mole per dn cube to 3 SF. So these are CB. So let's go to question number II. Question II says you should find the constant of A in mole per dn cube, the conc of A in mole per dn cube. So let's go to the whiteboard. So we're looking for Ca here. Our Cb have been obtained previously as 0.0566 mole per dn cube. Our Va is given to us also. The value of our Va is, from our titration table, is 20.30, that endpoint. Our Vb is 25.00 cm cube. Then the mole ratio of A to B is 1:1 for the balance equation. So you quote your titration formula CAVA over CBVB equal to NA over MB. Having done that, you make CA the subject. So CA becomes CB times VB times NA all over VA times MB. Making a substitution, the value of our CB is 0.0566. Our VB is 25, bottom of the pipette. NA is 1. VA is 20.3. This is the endpoint for your titration. And MB is 1. When we solve this out, we're going to have 0.0699 mole per dn cube as our molar concentration to 3SF. Question III says we should find the solubility of B at 25 degrees Celsius. Solubility of B at 25 degrees Celsius. So let's go back to the equation up. To the equation, they say that solution B is prepared by dissolving 1.50 gram of sodium carbonate in 250 cm cube at room temperature and diluting it to 1000. So let's mark 250, very important, and also 1000 or 1 dn cube. With this, we're going to calculate what we call the dilution factor before we go to solubility. So for this, solubility of B is obtained by using CB, that the constant of B in mole per dn cube times what's called the dilution factor. So how do we get dilution factor? Dilution factor is nothing but volume of solution after dilution all over volume of solution before dilution. Before dilution. So if you look at the equation we read out, the volume of solution after dilution is 1 dn cube, which is 1000 cm cube. The volume before dilution is 250. So the solution was prepared by dissolving 1.5 gram in 250 cm cube and dilute it to 1000. So divide this, you have the ratio, you have 4, that is the dilution factor. So solubility of B, following the formula above, will now be equal to CB, which we got as 0.0566 times 4, which is the dilution factor. So let's go to our calculator and then work out the answer. And that will give us 0.266 mole per dn cube to 3 SF as the solubility at room temperature. So now go to question IV that says mass of sodium sulfate obtained by evaporating 1 dn cube of titration mixture at the end of the reaction. Mass of sodium sulfate obtained by evaporating 1 dn cube of titration mixture at the end of the reaction. So let's go to the board. So first of all, write the equation for the reaction. H2SO4, which is given to you on the paper, plus sodium carbonate, giving us sodium sulfate, plus water, and then CO2. So we need this equation to solve it. So work from the stoichiometry reaction. The stoichiometry means the balance equation. So this is the sodium sulfate which you're looking for. We'll connect sodium sulfate to any of the reactants. We can probably use H2SO4. 1 mole of H2SO4 give us 1 mole sodium sulfate. When I say 1 mole of H2SO4 produce 1 mole of sodium sulfate. So since we are dealing with 1 dN cube of the mixture, we use the Ca of the acid concentration, which is 0.0699 mole of the H2SO4, will still give us, by proportion, 0.0699 mole of sodium sulfate. So the concentration of sodium sulfate in 1 dN cube is the concentration of sodium sulfate in 1 dN cube is 0.0699 mole per dN cube. So having done that, we find the relative molecular mass of sodium sulfate, or its molar mass, sodium sulfate, using what is given to us in brackets. Sodium is 23, multiplied by 2, sulfur is 32, and loss is 16 times 4. That gives us 142 at the molar mass. So having obtained that, we know that concentration in gram per dN cube, which is the mass in 1 dN cube, which we're looking for sodium sulfate, given by C, which is concentration in mole per dN, which we got as this, times the molar mass. So that becomes 0.0699 we got in the calculation times 142, the molar mass of the sodium sulfate. And that will give us approximately around 9.94 gram per dN cube. So this is the mass of the compound that will be recovered when you evaporate 1 dN cube of the solution. So we have come to the end of this endpoint determination of NECO June 2024 examination, internal examination. So if you are having any questions, you can send your questions across on the YouTube channel. We will attend to you. And then also, if you are not subscribed to the channel, as we used to say, tap on the channel's button, because you gain a lot from subscription. When you subscribe, you're not losing anything. When you subscribe to the channel, and we'll have, because before the examination, a day to the examination, we're going to do a general overview, review of what we have done. So when you subscribe, you're seeing the reviews, you're seeing comments. You don't just jump into the channel and jump out. And as I said, as a student, you have these questions with you, go through them. The values can be changed, but the method remains the same. Go through them. If I use 0.5 in the calculation, if I use 6.2 grams, they can change it and use a different value. Just go through the calculations and see how it's been done. The method remains the same. If your endpoint agrees with our own endpoint, use it. If it doesn't, then use the teacher's endpoint and follow the same process to do your calculation. Then another area that is very important that you should go into, which we didn't have time to look at, is water of crystallization, because sodium carbonate can be hydrated. So when it's dissolved inside water, it can form washing soda. So they can give you a question on water of crystallization, whereby they give you something like sodium carbonate and then put .S water with the water molecule hidden. At the end of the day, you have to find the number of water of crystallization in the question. So you go through it and do it. Then you have time. If you have time, you can still do it in this YouTube channel to show you how to calculate this water of crystallization. That's what we say. You should subscribe. That you follow us along as we do this. So stay connected always. Share our videos. Share our video. Don't learn alone. Share to your friends. Share to your teachers. Let them go through it and then help you to understand.